Today, we're pleased to introduce Dr. Renato Figueiredo, sorry about that, a professor in the School of Electrical Engineering and Computer Science at Oregon State University, where he leads research on distributed systems and cyber infrastructure. Prior to starting at OSU, Dr. Figueiredo graduated with a PhD from Purdue University in 2001 and joined Northwestern University as an assistant professor also in 2001, and subsequently the Electrical and Computer Engineering Department at the University of Florida from 2002 to 2024. Dr. Figueredo has a broad and extensive research background, and some of his research interests include CI support for interdisciplinary science-driven solutions to pressing issues in the environment and society, in particular freshwater resources and biodiversity. We're excited for his talk today on some of his team's work around developing natural language-based AI agents for environmental data exploration and analysis, including AI agents for working with NEON data. So with that, I'll pass it over to Dr. Figueiredo, and thank you.
Thank you, Bridget. Thank you, Bobby, for the introduction. Thank you, everybody, for coming. Let me share my screen and start my presentation. Can I get an okay that it's visible?
Looks good.
Thank you. So, as Bridget introduced, my work has been primarily at the interface of cyber infrastructure and computer systems and applications in biodiversity and environmental science. And today I'm going to talk about work that is beginning to leverage natural language and large language models and agent technology to help users in exploration and analysis of data sets from multiple providers. So key motivations here is repositories and infrastructure like NEON, as well as LTER and LTREB and repositories like EDI. We have an increasing availability of data that's coming in from environmental sensors. So these are incredibly valuable for research. And in particular, there are many interdisciplinary research questions that involve not only environmental sensor data, but connecting that to other types of data, for example, repositories on biodiversity like GBIF and IDIC-Bio. So there's a lot of data available in repositories that serve that data, but it still remains challenging for researchers to explore, access, and analyze data from these repositories in a reproducible manner. There's a complexity associated with using the data. So how to find the data, how to process the data, how to harmonize, and how to combine the data for analysis. So we're in a situation where there's multiple data sources, each data source with a specialized type of data sets and interfaces. And users, researchers, and users would like to create workflows for analysis. And these could be one-shot workflow for a paper, or these could be recurring workflows that run, for example, for automated forecasting systems. And I'll talk about one example later today. So from a user perspective, to work with different data sets to tackle a research problem that's interdisciplinary and crosses multiple data set boundaries, the users have to work with different interfaces or application programming interfaces or APIs. So the user needs to know how to query data from these multiple repositories, download and extract the information that they need for their particular application, and then harmonize and synthesize data as part of their analysis workflow. So that entails writing code that performs these different steps. Some of the steps being more connected to a particular data provider, and some steps might be more generalizable once the data has been extracted and preprocessed. But still, in addition to that, the user needs to execute and ideally be able to set up a system that can be reproduced by others who want to follow the same approach. And in some situations, again, automation is desired. For example, for workflows that you would like to run on a timer, let's say once a day or 4 times a day or once a week. So the automation of this, so that it doesn't require human intervention for um, launching these workflows every time that you need to execute them, are an extra burden on the researchers. So in many ways, users who wish to perform these kinds of analysis have to learn a lot. Have to learn how to talk to different providers of data. You have to spend time writing code to extract data from these different providers with their different APIs, and then process that code, harmonize, integrate, and perform the analysis, and eventually deploy this somewhere, ideally not on the user's own computer, but in an environment that others could reproduce, for example, in a cloud computing environment, in a way that the same workflow can be executed by others. So as you can see, the user here is not very happy. There's all these things that they need to do. What we're trying to accomplish here is improve this situation by developing a combination of AI agents that expose to the user a natural language interface that simplifies the way one can interact with these systems. And the end goal is to eventually allow the automated development of the most of the work that needs to be done in the coding side and also in the automation of workflow side for reproducible deployment in cloud computing infrastructures. So overall, the main goal here is to really reduce barriers to researchers to explore, analyze, and synthesize environmental data and accomplish the kind of research that they love to pursue. So the agents here, and we'll talk a little bit more and show some examples of what an agent looks like. But the agent would be the um, the helper for the researcher that will help in many of these tasks that, again, today still require a significant investment of time. So talking to different data providers with their different interfaces and exploring data in these providers while exposing to the end user a more friendly natural language interface. And using code generation, leveraging LLMs also to generate pieces of code that you can stitch together in these workflows. And in addition, allowing for these workflows to be composed and deployed in a way that is reproducible in a cloud computing infrastructure. So with this, I'm going to talk about where we are in this vision. This is sort of a long-term vision, but we're working towards this, and I'll show you some of the efforts we've been doing in multiple dimensions of this problem. So I'll start with AI agents and their uses in data exploration and code generation. And examples that myself and collaborators have explored include the use of iChatBio, which is a multi-agent based framework that has been developed at the University of Florida. My colleague José Fortes with iDigBio, and a student Michael Elliott, and an IT developer Manny Luciano. And examples with also Neon and EDI agents that my students here at OSU have collaborated with the iChatBio team to show the ability of these agents to not only access biodiversity data, but also environmental data sets. And then I'll talk about work that my team has done, and also in collaboration with ecologists, on cloud computing workflows. So that includes the FASTER system, which is a software that aims to simplify the deployment of function as a service, or FaaS style cloud computing. And I'll dive a little bit deeper into that soon. And an example of that in the FLARE project with my colleagues at Virginia Tech. So to start, let's look at what an AI agent is and what it can do. So one definition of an AI agent is a software system that can use AI to pursue goals and complete tasks on behalf of users. So these could be, again, the goals could be to explore data, to extract data, or to generate code that's used for analysis of data. And these agents can be seen as assistants, AI assistants that collaborate with the users, again, with a natural language interface and performing tasks by responding to this a conversational interface with the human in the loop. So they can reason and take action on the behalf of the users with their supervision and their input again with the natural language interactions. So let me go through an example scenario. Let's say you'd like to use data from Neon or EDI or other data providers in your research. So many of the steps you might need to do manually include finding the user interface or an API to program against, to query data sets and discover data sets that might be relevant to your work. And then you need to fetch and understand the metadata that's associated with these data sets. Download the data sets themselves, check, remove errors, duplicates, things like that. And then creating code to process the data in addition to code to discover and download data. And each one of these steps takes work. And if your work cuts across multiple repositories, you have to repeat that for different data sets, and it is a time-consuming process. Now, large language models like ChatGPT, Claude, Llama can help. You can begin to, and all of you probably have used systems like this in the past, and they're very powerful in providing answers to queries that you may type through a chat interface with an LLM system. So they can help in many aspects here, but there's limitations with existing systems. They're very general purpose, and when it comes to being able to access and process data from these different repositories, they can fall short. So for example, you could go to an LLM like ChatGPT and ask about, let's say, you're interested in stream temperature data in the Andros Research Forest, which is a forest here near OSU. And ChatGPT may give you quite a bit of information about this. This is information that's available through on the internet, on the training data set that this LLM has been built from. And this is already a starting point. So it does locate some of the data sets that have this information. But if you try to go deeper into the information that you're trying to retrieve, for example, a list of specific station names from one of these data sets, this is something that the LLM is not going to be able to accomplish on its own. You may try multiple avenues, a browsing tool, but it's unable to use the EDI APIs, for example, to retrieve that data from the repository. It gives, in this example, it gives you a command. Here's how you could download this information, but it doesn't download for you and it doesn't process that for you. It sort of pushes that responsibility back into the user. So LLMs can help in processing, in discovering data, but there's limitations, again, tied to the inability for the LLM itself to generate API invocations against these different data sets and retrieving the data sets and processing metadata for your further actions. But again, there's significant power in the LLMs. What we're looking at is a system that leverages LLMs, but also includes the ability for composing a distributed system with multiple agents, where these agents have the capability and the knowledge to query and extract data from these different providers. So you can still expose a user interface with a natural language interaction to the user, and you can still use an LLM to parse user intent and to help in the generation of queries that the agents are going to provide for these different data providers, but the process of generating the query and extracting data and downloading data is handled by these agents, not by the LLM itself. So the LLM here could be a commercial cloud-based LLM like ChatGPT, or it could be also potentially a open source LLM that you run on your own infrastructure. So one of the efforts we've been doing along these lines, again in collaboration with iChatBio, is to investigate the ability of these agents to be able to interact with existing environmental data providers. In particular, we've implemented a prototype for both EDI and EON agents, and the group at UF, again, that's Joseph Ortiz, Michael Elliott, and Manny Luciano, have developed and deployed a framework that makes it possible to plug in these multiple agents and expose the multi-agent system to end users. So you can think of the technology here in iChatBio as sort of the backbone of a system where you can plug in agents of different types, and we've collaborated specifically on the agents for environmental data sets. If you're curious about this, iChatBio.org is where the main iChatBio system is hosted. It doesn't host EDI and EON agents that we've developed as prototypes. We run those in a separate instance, but it does provide several agents for, in particular, for biodiversity data sets like GBIF and IDIC-Bio. The EDI and EON agents have been developed here at OSU by my students, Zehua and Laura, in collaboration with my colleague, Julia Jones at the H.D. Andrews LTER. So let me show you what the user interface looks like for these agents to give you a feel for what kind of interactions a user might have to be able to access these systems. And this, it looks and feels like many other chat interfaces that you find with LLMs. You can, the user can type a query, for example, here, are there any data products related to our temperature in the Neon repository? Now, this agent, this system is able to process that data process that query using an LLM, and then invoke the proper agent that can help satisfy that query. In this case, the sort of the front end agent will look at your request and determine that you would like to, that you'd be a good idea to use the Neon specific agent to search for this data. So the Neon agent will then be invoked and will use its own logic to query data from the Neon portal. This particular case, the agent is finding a set of data products related to this query and showing a summary of the top 10 relevant data products that were returned from a keyword search. All of these queries can be retrieved later on by the user as artifacts. So the agent generates artifacts that include, for example, the list of data products or the list of or code that it generates along the way. I'll show that in a minute. So here, again, this came from querying the Neon portal. If you'd like to dig deeper into one of these data products, for example, this particular data product, the agent is able to use the Neon API and the GraphQL interface to fetch metadata and summarize metadata from this particular data set. So this involves retrieving metadata and summarizing it on the agent side. And you can go one step further and ask, what variables are available there. And again, these are the types of queries that an LLM by itself would have a hard time digging into the data to find this information. But the agent, in this case, is aware of finding, has been programmed to find where the variables are described in a Neon data product and extract that information and summarize that back to the user. With that information, the user could ask the system to generate code. And here, the code generation, again, we're using an LLM to generate code in the backend, but that generation of code is guided by the information that was retrieved in a previous data exploration query. So here, for example, we're asking to see a plot of a time series for a particular site and asking for the Neon agent to generate this code. So the process here, the agent creates a plan for retrieving the data and generating the analysis code and also executing the code. And if there's any problems along the way, retrying, generating the code and running the code until the code is successfully executed. So the steps here for code generation, this to a large extent is offloaded to a separate agent that is based on a technology called Codex, which is an open AI-led code generation agent, but it's an open source product and it doesn't tie necessarily to OpenAI. You can use with different LLM models, but it basically is a system that you can invoke requests to generate code and to execute code in a sandbox. So this is integrated with the system here in the way that as part of the request for code generation, the agent provides information to the code generator about, this is the data set that we're going to use. This is the variable that I'm interested in. This is the site that you're interested in. This is the metadata describing the data set. These are the data tables to look at. And with that information, the agent generates code, executes the code, and it shows back to the user as artifacts the code that's been generated. In this case, is a Python code, a data set that's resulting from this analysis, and a plot. So the plot for this particular case would look something like this. This is, again, generated by the code generation agent all through these conversational interfaces that I showed in the previous steps. So this is again a prototype, and the functionality is still limited. We're able to explore, download, process metadata, and generate code for things like simple analysis and visualization. There's a lot of work to be done, in particular, once you start composing data, combining data from multiple sources and building workflows. These agents will need to have more reasoning capabilities and more context to be able to accomplish that. But I think that this looks very promising as going from a conversational interface to some insight into the data that would otherwise require the user to spend quite a bit of time learning about an API and programming how to extract and analyze data. So just switching to how do we get from this to workflows, I'll talk a little bit about a workflow system that we've been developing here at OSU in the example for short-term ecological forecasting. And these are not yet fully integrated with the agent work, but that's the direction we're going. So Flare is a motivation for this project. Flare is a system that's been led by Kaylin Carey and Quinn Thomas at Virginia Tech, and I've been collaborating with them for more than 10 years now. And basically, it's an iterative forecasting system. And by the way, it can use data from Neon. It can forecast lake variables like lake temperature at different depths for the Neon lakes using Neon data. But basically, the system starts with observations. Again, these could be observations from Neon and a weather forecast and drivers for the inflows and outflows of a lake. It runs a model, ensemble model to make a forecast into the future, visualize the outputs, archive that, and assimilate that data for updating model conditions for the next day. So this is a process that happens on a daily basis. So again, this is a case where the execution of this whole workflow is important to automate. So we've implemented this work in Flare. I point you to the Flare website if you're interested in seeing some of the outputs from these forecasts. And what we've learned as part of this project, we started with, we built a workflow for Flare, and we moved from that to how can we generalize that workflow that we built here to a framework that allows other researchers and practitioners to develop similar workflows. So that led us to a project called FASR, and that is function as a service. And it started with R, hence the name FASR, but it has been extended recently to support Python and Julia as well. And the key idea here is that we want researchers to write these workflows in a high-level language. So every piece of the workflow can be written as a high-level function in one of these languages, and that these workflows can be deployed on cloud infrastructure without you having to manage any servers. So for example, using GitHub Actions with a low barrier to entry, some of these forecasting workflows many of these run on GitHub Actions and also run on different platforms like AWS Lambda or Google Cloud without having to change your code. So you can write the code at a high level, and where you deploy these workflows is a separate question, but you don't have to change your code to map to a different provider. So an overview here of the system, you can write your functions as, again, functions in R or Python. You can think of these functions as functions that read data, compute something, write data back, and then the function terminates. The data could be files that you download from your own repositories, or they may come from external repositories like we do with Neon. And the workflow stitch together these functions in a graph that describes the ordering, the dependencies of these execution in a way that allows you to compose them in an ordered, structured fashion. In the backend, these functions run in containers. You can think of these as Docker containers that make it easier to reproduce the execution across these different providers. And the function code, the functions that describe the different pieces of the workflow can be dynamically pulled from GitHub repositories as the workflow progresses. So to give you a little bit of perspective on function as a service computing, this is a style of cloud computing. One example is Amazon Lambda, but there's other examples, again, like GitHub Actions, which is basically based on this idea of a serverless framework. And the analogy here is, the traditional cloud computing, where cloud computing started, right, with Amazon EC2. You can think of this as analogous to renting a car. You can rent a server in the case of cloud computing, like you rent a car, but then you have to manage that server, right? You have to install software, you have to apply patches, you have to keep the server up and running if it crashes. There's a lot of management that goes in. Just like when you rent a car, you have to navigate, you have to drive, you have to fill in the tank, deal with any hiccups along the way. In the serverless model, the idea is you work at a higher level of abstraction, you write these functions, and you don't need to manage a server. And again, this is analogous to a ride share where you hop into a car and you tell where you want to go, but you don't have to manage that car. Somebody else is managing that for you. And it's particularly helpful in environments where you have short runs and you don't have to pay the cost of running a long-term server. On the storage side, this is for the computing side. On the storage side, we really focus on a de facto standard called S3. S3 buckets are used by many data providers already, and it's basically akin to a Dropbox, but with an API that applications can use. And our system abstracts these S3 buckets in a way that you don't have to worry about these APIs. You can work with these buckets at a high level of abstraction, like get a file or put a file without having to concern yourself about how to actually get that to work with all sorts of different S3 servers that exist out there. And abstraction here maps to dealing with files that can be read or written by these cloud computing tasks. So from a user perspective, it boils down to you writing functions with arguments, and these functions can bring inputs and outputs from S3 buckets or from inputs from different repositories. And these functions can be written by different users and shared into code repositories, so they can be reused by others. And they can be composed into more complex workflows that sort of orchestrate and integrate multiple of these functions to accomplish more complex logic. And once you have this code developed and composed as workflows, whether you run this on a GitHub infrastructure, AWS, or Google Cloud, doesn't change the code or the workflow itself. It changes just a little bit of configuration. You need to have your credentials ready for these different providers, but it's not a change in the code or in the workflow itself. So that's one. We wanted to have a system that's not tied to a particular provider and that locks you in with that particular environment. This can also run unattended with timer events, for example, a daily timer or a timer, an event based on data availability, and can scale as needed. The benefit of using cloud computing is if you start with one lake today and you need to grow to 100, 1,000 lakes tomorrow, this is possible. You might need to pay for a non-free tier resource, but scaling is much easier to accomplish. So one example that we used in the workshop with the ecological forecasting initiative last year. So you can write R functions, for example, that get data and do different forecasts for different variables and combine these forecasts into a single visualization, for example. This can be written as separate functions. Each of these functions, again, in R or Python or Julia, could be available in a repository and accessible to execute. These workflows, it can think of a graph that doesn't have cycles, is a direct acyclic graph that basically describes, you need to get data before you run the forecast, but the two forecasts can run concurrently. And the combined forecast needs to wait for the two forecasts to finish before moving forward. And all of these communicate through a bucket in S3. And all of these run eventually when they get invoked in the cloud run as containers, like Docker containers, in a serverless manner. You don't have to manage a Linux server. And the different functions communicate through this bucket to pass information other than arguments in the form of files. So with that, I'm going to wrap up, and so we have time for questions. There's plenty of future work here. There's several improvements to the agent framework that our group and the University of Florida group has been collaborating on. This is a technology that's been changing rapidly. So LLMs and agents are a fast moving target, but we're interested in building orchestration reasoning at a high level to be able to run queries and to combine data for analysis across multiple data sets. Working with the natural language interface to help the user clarify and specify unambiguously what they would like to do. Addition of multiple agents to help improve the quality of the data that's coming back from this process. So agents that can look at the output of another agent and be a critic in the sense of parsing that output and verifying that it matches an expected type of information that you'd like to deliver to the user. And a very challenging problem here is validating, especially the code and the code execution. At this point, it relies primarily on the user to look at the code and execute the code and verify that the code works according to what they would like to do. And then having the agent framework itself be able to generate workflows and compose them and deploy them in cloud infrastructure as agents to again reduce further the amount of manual work that might be needed from an end user, a researcher in environmental sciences to be able to accomplish interesting analysis. So with that, I'd like to thank you all for your attention, open for questions, and leaving some of the links here for some of the systems I talked about today, and acknowledging my collaborators in these projects. And again, thank you for your attention.
Thank you so much, Renato. We did have a number of questions come in while you're talking, so I'll start with those. But yeah, I think we're all super excited about this work. And personally, I've used AI agents in my own work and see how much it can really accelerate things. And so I think for the Neon community, this is really the future. So I'll go ahead and get started with some of the questions that came in.
Mhm.
So our first question is, How general could these agents be? Would it be possible to ask something like, quote, please find as many publicly accessible data sets of leaf area index as you can, download the data, and make a map of their geographic distribution? And then this person has tried something similar with Manus, but it burned through all his tokens and crashed. So that's the
Yeah, yeah. Well, I think it's possible to be quite general, and again with the limitation of if you're using a commercial LLM, you're going to have potentially to worry about cost. I think, as technology improves and some of that percolates to the open source LLMs, it's going to be possible to host the LLM infrastructure itself, a good LLM and reasoning engine locally. So you'd have to pay the cost of hosting a system, but not the cost of paying for token processing. So I think that the main challenge here is that some of these agents, some of the data that you would like to discover, if the data itself is not available through an API, or if the API that is available is not quite agent friendly, so to speak. So you may have to download data and look inside the data. You may have to download a lot of data to find just a little bit of information. It might be inefficient. So I think these agents will be able to be quite general, and I think that's going to become that moving towards that direction will require that data providers will have APIs that are agent friendly that allow you to discover data with a rich API that doesn't require downloading large data sets for data exploration, and potentially again with the use of open source locally hosted LLMs to rein in some of the cost implications. Yeah.
Thank you. Our next question is, how are data harmonized if searching across repositories, and where would this happen in the workflow?
Yeah, we haven't done any, we're not at that point yet. The idea, and I'm quite interested in the topic, and I'd be happy to talk to you and the person who asked the question. If you're interested in this, I'd be happy to follow up with you offline. But so how it is harmonized, I think it's going to be a function of, what kind of work are you trying to do, right? You need to harmonize in terms of, you know, sampling location or time, or use ontologies to map information that's described for one data set into a representation that's available for another data set. So I think these would be the nature of the harmonization will depend a lot on the application. The way I see this, where this would happen, in my view, would be these agents would have the knowledge to, or the ability to generate code that does different pieces of this process. So agents it's harder to generate code, a large, um, a large, extensive piece of code from a prompt without the agent being, losing context or being too asking the agent to do too much. But it's simpler to generate smaller, well-defined functions that work, have a single purpose. And I would see, the direction here would be to have a growing sort of library of examples of data harmonization. Some of these might be human generated instead of AI generated, but you can have template code that the AI agents could use as starting points to generate specific code for a particular data set. There's technology called retrieval augmented generation that can be used as a starting point for this, but again, we're not there yet. We haven't really done the harmonization and the workflow integration at this point, but that's the direction we're going for. I'd love to hear use cases and work with the community on this because we need to learn more about this as well.
Great, thank you. The next comment and question is, thanks for the talk. Very cool tools. How do your agents address data provenance? For example, do the agents output proper citations for EDI or NEON datasets? And do the agents recognize, for example, provisional versus released NEON data and make that known to the user?
Yeah, that's a great question. I mean, the agent does show everything that it's doing to the user, including, um, you know, a log of the uh, even the API queries that it's issuing and the URLs of the data sets that it's downloading. I didn't show in the examples here, but if you were to, let me see, like if you were to click on this box, one of these boxes here, fetching metadata for GraphQL for DP1, etc., it will show you the actual query that it used and the data that it's using. And this is saved as an artifact that you can go back and reuse. So that's the level of provenance that we can provide. Now there's two challenges here, right? If you do multiple steps, the system is providing you the artifacts that it's using, but you would want to, eventually have a summary of all the artifacts that were used in the sequence of steps that you create your workflow. There's more work to be done there, but we start from a foundation of the keeping the steps that have been done as artifacts.
Thank you. And then we have a somewhat longer question from one of our scientists, Sarah Paul. So, Sarah, if you're available, I might just have you ask, and then Darcy, you may need to unmute.
Give me 1 second. Since she didn't request it, I have to find her.
Oh, okay.
Got
We
it.
can we can go ahead with there's another question and then go back to that.
Is that working now?
Oh,
Yes.
yeah.
Okay, great. Thank you so much. This was a really exciting and fun talk to hear about, and I like imagining all the possibilities. And I think one thing that jumps to my mind as I'm listening to it is thinking about some of the distance that's created between the user and the data. And I think it's a challenge that Neon already has, right? When with other people collecting the data and then end users trying to analyze it in the way that it's intended to be used. So sometimes in the process of looking at the raw data itself and how it's organized, you can identify pitfalls like you might want to exclude certain samples or check remarks and things like that. And I'm wondering if you've thought at all about ways to build in safeguards that might help data users use the data more appropriately and avoid misusing data out of just a lack of familiarity with how it's collected. And I put a little example in here in case it's hard to imagine exactly what I'm talking about. Is the Neon mosquito data set collects individual counts, right? But to accurately get the abundance of the organisms, you have to correct for the subsampling piece. And I'm just wondering if you've thought at all about, is that on the end user to figure those kinds of nuances out and code appropriately or write appropriately, or is that something that the models are able to?
Yeah, no, that's a great question. I think, today that, the stuff I presented today, this would be part of what would be on the user to handle or at least prompt the agent to handle. So, there's the possibility that the user would ask the agent, for example, can you generate code that performs XYZ on the data, with the intent of addressing one of the issues that you just brought in. But they would need to know to ask that question, right? And so I think that's an open-ended problem, and that's going to be a challenging one. I think on the automation part, what can be done, as a safeguard here would be to have, with expert knowledge, right? Knowledge that is specific to Neon or somebody who understands the mosquito data, like you mentioned. It is possible to add agents that will verify pieces of this workflow. So you could have, for example, a step that would include an agent that's familiar with a particular type of data and looks for, potential use of the data that may not be what the user intended. So that would fold into what I mentioned, the critic agents, which we are interested in pursuing, but there's no critic agent in the system right now. So that would be the place that I would start. But it is this whole user AI interaction and sort of, like you said, providing even more distance from the data. We have to be mindful of what that means for the proper use of the data. So I think that is a big question in general that will take some time for the community, not just the AI agents, but also the community to think about how do you represent this information in a way that a user or an agent can process, and what would be tasks that can be automated to help mitigate that.
Absolutely. Thank you so much. I appreciate that.
Thanks, Sarah.
Yeah, I think Sarah brings up a good point because I think one of the challenges we've seen is that a lot of folks using our data don't read through all the documentation, or it's just there's too much documentation to sift through. So in one aspect, these AI agents can really facilitate that process. But then on the flip side, you might again miss some of the nuances of that. But yeah, so the next question I think is also pretty relevant. There's someone who asks, is there any prompt for iChat Bio to achieve its best practices?
So there's some examples in the iChatBio interface. And again, iChatBio, if you go to ichatbio.org now, you're going to see primarily biodiversity data. The neon stuff that I mentioned today is not in that main iChatBio site because it's a prototype. But I would suggest starting with the example prompts that are in the system. And if you're interested in, trying things out, right? Trying things out with a natural language interface and see where you may be hitting a block. And I would suggest contacting the folks at iChatBio if you're interested in pursuing that further. But yeah, I will start with the examples on the landing page. Yeah.
Thanks. And then we have another question. Thanks for the session. I use the Google Cloud platform to monitor ecosystems over time. Google Cloud already connects with Earth Engine to collect geospatial data. How could AI agents be used to help collect or augment data collection?
Yeah, I'm not familiar with Google Earth Engine data and APIs, but you could, in principle, it is an API that an agent could use to automate some of the processes here. I'd like to understand a little bit better what is it that is like it's difficult to do now with the existing infrastructure. I think the AI agents can, the part of the work that we've been pursuing here, sort of the the goal or the assumption is that it might be a user who's not familiar with any of these interfaces and wants to build workflows that do not exist yet. Now, how an AI agent may help with an existing workflow, I think that's a slightly different story. So yeah, I think I'd have to learn a little bit more about the use case here, but I'm primarily focusing on how to get new workflows going rather than augmenting existing workflows.
Thanks. And then we have a couple more questions that just came in. Are there limits to the compute resources used in the backend? For example, all of NEON's airborne hyperspectral data collected across all sites and years may exceed 20 terabytes.
Yeah, yeah, yeah. The kind of resources we have for this now are not ready for this type of massive data. We're mostly working with, at this point, with biodiversity specimens. These are Darwin core records or images. They're not going to be at that magnitude or environmental sensor time series. We're not dealing with large remote sensing data. I think that requires an infrastructure that's capable of dealing with that. So that takes the cyber infrastructure beyond the capacity we have now. So I don't think it's a fundamental limit of the approach. Agents can be designed to automate the process of run these large batches of data, but you're going to run into the issues of how do you bring that data in, and do you have enough storage for that, and how to allocate resources for different agents for different users. And we're not at the point where we're dealing with this type of large data. But again, I think in summary, it's not a fundamental limitation, but definitely there's always going to be finite resource limitations that can bound what's possible here.
Thanks. Yeah, it sounds like maybe a first step there would be downloading metadata relevant to that and starting from there. And then a last question we have, I think, and then we'll have Bobby wrap up. But how have these agents handled data quality flags for the data sets and communicating those quality flags to the end users?
Yeah, so I think this would be part of what you would have to describe to the agent. So agents you can think of the agent can be configured with its own set of instructions. So an agent for Neon, for example, you could augment it, and we haven't done that in our prototype yet, but it could in principle augment it with a description of what the data flags are and how to handle them for a particular, for as the agent is generating code, for example, to process data, which could be, for example, flag to the user that these are there's these types of data flags here. How would you like to handle data that is flagged in this particular way? So I think that the agent would need to be aware of these flags through prompting and configuration of the agent. And the process of automation of dealing with these data flags, for example, removing data that matches a flag or interpolating data that matches a different flag, this would be on the agent, on the side of the agent generating code that processes the data. So I don't see the agent itself cleaning the data, but I see the agent generating code that would clean the data or would handle a particular data flag. But the agent would need to have knowledge of what the data flag means and how to handle it. Yeah.
And we did just have one more question come in.
Yeah,
Bobby, do you think
if we can answer it quickly. We've got about
Okay.
3 minutes, so.
Okay. And then one person asks, how much money was spent when you asked the agent to access the Neon, all of their aquatic data, abundance and size time series, and how many tokens roughly?
Yeah. So, this interaction that I showed here was again a search on the Neon data portal with a sort of a automated, like a headless browser as part of the agent. And then the GraphQL queries, and then the use of the agent for code generation. So the whole process on the token side, on the ChatGPT side, if I remember correctly, it's like 35 cents to do the processing of the natural language queries, generating the queries for Neon, summarizing the data, and generating code. And yeah, less than 50 cents.
All right, so I want to thank Renato for giving us his talk. Thank you, everybody, for attending.